So in Chapter 4, this is our last, full unit, if you will, in college algebra. So yay, we made it to the last unit. Chapter 4, we start out with working with inverse functions, and you're probably going to go, okay, and kind of get through the lesson and be like, okay, that's fine, whatever. But what happens is as we work our way through the chapter, we kind of see some connections between inverses and what we call exponential functions and logarithmic functions. And by the end of the unit, there's some really cool connections that happen, and we're able to see some really cool word problem situations in the real world that actually get used, like with medications and half-lives. You may have studied that in a chemistry class or something, but it's going to make a lot more sense, some word problem application type things. So just kind of bear with me as we work our way up to some of those involved problems, but it is pretty cool when you see it all work out. So, inverse functions. If you just think about what the word inverse means, inverses sort of means opposites, okay? That's a lot of times what people think. I don't know if that's exactly what it means, but that's how people kind of interpret it, what they think in their heads when they hear inverse. For instance, adding and subtracting are inverses. They undo each other, okay? Multiplying and dividing are inverses of each other. They undo each other. Squaring something and taking the square root would undo each other. They are inverses of each other. So when we start talking about functions, okay, like, f of x equals 3x minus 8 or whatever, some kind of function, a graph that we could draw, the inverse or kind of opposite or undoing of it would be if we traded our x and our y, okay? So if we think about f of x as being a y equals 3x minus 8, if we traded the x and the y, that would be the inverse. So the inverse would be x equals 3y minus 8. We just traded the x and y. Now, this is not really a convenient format that we can graph. We would prefer it to be in that, y equals mx plus b format. But technically, this is the inverse. Trading the x and y does that. Now, if you think about domain and range, well, domain is the x, and range is the y. So if you trade the x and y, you're really trading or swapping the domain and the range, okay? So the domain of an original function would become the range in the inverse and vice versa. So I'm going to kind of do these out of order here, but let's look at this set of ordered pairs here, okay? Well, our domain, our x's, are the 2, the 4, the 7, and the negative 2. The range, the y's, are the second numbers, the 1, the 2, the 3, and the 1. When we trade them, because here's our original, when I trade them to get the inverse, the ordered pair that was 2, 1 would become 1, 2. The ordered pair that was 4, 2 will become 2, 4. We're trading the x and y, the domain and the range. The ordered pair that was 7, 3 in the original will become 3, 7 in the inverse. And the point negative 2, 1 in the original will be 1, negative 2 in the inverse. All I've done is trade the x's and y's. Okay? Anything that was an x in the original is now a y. Anything that was a y in the original is now an x. You could say we swapped the domain and the range. Okay. This right here is called a mapping. And what that means is they've given us the x's. Now they're calling it domain instead of x, but we know that's what that means. So in the original, we had the ordered pair A3. 3 was the x. I'm sorry, A was the x. 3 was the y, the range. Okay. In the inverse, that ordered pair will be 3A. We just reverse it. In the original, we had the point B6. So in the inverse, it'll be 6B. The original had the point C3. So the inverse will be 3C. And the original had the point D9. So the inverse will have 9D. We just reversed the x and y. Okay? Now, remember back in Chapter 2, I believe, we talked about how what it meant to be a function. We said, well, if something is a function, then it passes the vertical line test. All the x's are different numbers. So, for instance, if I look at these original order pairs here, all the x's are different numbers. 2, 4, 7, negative 2. The x's are all different. Okay, so it's a function. Okay, the x's were all different. But notice the inverse is not a function, because when I look at the x's on my inverse, 1, 2, 3, 1, the number 1 for x gets used twice. So the inverse is not a function. Okay? Because the x's repeat. Now, if I'd really been thinking about it, I bet I could have figured out that the inverse was not going to be a function by looking at the original. So remember, the x's in the original become the y's in the inverse, and the y's in the original become the x's in the inverse. So if you look at the y's in the original, notice how the original had a repeat of y's. Now, the original's still a function, okay? But because there's a repeat in the y's, we know that when we get the inverse, it will have a repeat in the x's and therefore not be a function, okay? Let's look at this first one. The x's were all different, A, B, C, D. The original is a function. The y's, however, had a repeat. There was a repeat of 3. So even though the repeat is in the y's for the original, when we get the inverse, that repeat is in the x's. So in these two cases, even though the originals are functions, because x's do not repeat, inverses are not functions. Because their x's do repeat. And we could make a note for ourselves that the original y's repeated. So we could use that as a little shortcut to make a prediction about inverses. If the originals have a repeat in the y's, then that means the inverse would have a repeat in the x's and therefore not be a function. Okay? That's a new vocabulary word here, one-to-one function. A one-to-one function means the original and inverse are both functions. Okay, so a function is considered one-to-one if both the original and the inverse are functions. In other words, the original has all different x's and the inverse has all different x's. Or another way to say it, the original has all different x's and all different y's. Because if it's y's in the original, it'll become x's in the inverse. Okay, so they're just saying, hey, if A and B are different, then f of A and f of B have to be different. They can't be equal to each other. Or this is another way of saying it right here. Okay? All right. Another way to check that is what we call the horizontal line test. You may remember the vertical line test. Vertical line test said that if you drug your pencil across it vertically, you never hit more than one point at a time. So functions pass the vertical line test. But if we think about a horizontal line test, hold your pencil horizontally and see if you ever touch more than one point. And if it passes the horizontal line test, that means when you find the inverse would pass the vertical line test and be a function. Okay? So a function is one-to-one if no horizontal line touches the graph in more than one place. All right, so let me give you some examples of that. So this is a graph right here, and it is a function. If you notice, if I take a vertical line, I never touch more than one point at a time. Okay, so it's a function. By the vertical line test, it's a function. Now I'm going to try the horizontal line test. I'm going to hold my pencil horizontally. Notice if I hold it horizontally, I never touch more than one point at a time. So it passes not only the vertical line test, but also the horizontal line test. So this means, yes, it's one-to-one. It's one-to-one because passes vertical and horizontal line test. The vertical line test told us it was a function. The horizontal line test told us the inverse would be a function. Since they're both functions, it's 1-to-1. Okay? All right, the middle one here. It is a function. It passes the vertical line test. If I drag a pencil across it, I never touch more than one point at a time. However, if I draw horizontal lines, I'm touching more than 1 point at a time, aren't I? So it's a function because it passes the vertical. But it is not 1-to-1 because it does not pass the horizontal line test. Okay, and then the last one. It's a function. If I drag my pencil across a vertical line, it never touches more than one at a time, so it is a function. And if I drew horizontal lines, I never touch more than 1 point at a time either. So it is 1-to-1 because it passes both the vertical, to be a function, and the horizontal line test. And I'm going to abbreviate that HLT for horizontal line test just to save a little time there. Okay? Okay, well that's great. We can look at ordered pairs. Or we can look at a graph and we can go, oh yeah, look, it's going to be a function, and yes, it's going to pass the horizontal line test, and the inverse will be a function, okay? But sometimes we don't have a graph, and we don't want to spend time trying to make one, okay? Or maybe we don't have a list of ordered pairs. Maybe we have equations, like on page 2 here. And they want to go, hey, are these going to be inverse, or are these inverses of each other? Or what is the inverse of some random equation, okay? So something interesting happens when you have 1-to-1 functions. Remember, 1-to-1 means both the original and its inverse are functions, okay? All right, so two functions are inverses of each other. So by definition, if f is 1-to-1, then g is the inverse if the following are true. And notice this is not the times dot. This is that little composition dot. So this is saying if f of g of x equals x, and if g of f of x equals x. So here's what this is saying. If we take the g function and we stick it in the f function, that will simplify to x. And similarly, if we take the f function and stick it in the g function, that will also simplify to x. If both of these things happen, then f and g are inverses of each other. Okay? This little symbol right here looks like a little exponent of -1. Okay? It means f inverse. That's how we say it. We don't say f to the -1. We say f inverse. That's what this symbol means. So if we are given a function f of x and its inverse, f inverse of x, then that definition implies that these two things simplify down to be x. F of f inverse of x will simplify to be x, and f inverse of f of x will simplify to be x. This and this mean the same thing. I just like to write it with the parentheses. I think people can see what that means a little bit better. Okay? Remember what we said a while ago about inverses. The domain of one becomes the range of the other. The range of one becomes the domain of the other. So the domain of f of x is the range of f inverse, and the range of f of x is the domain of f inverse. Okay, keep that in the back of your mind. We'll revisit that a little bit later. Okay, we'll look at an example and then we'll do some graphing in a little bit. Okay, so let's say f of x had this domain and this range, and we don't know what the equations are. We don't know what the graph looks like, but apparently this is the domain and this is the range. That means that when we find the inverse, remember this little notation looks like f to the -1, but it really is pronounced f inverse, then the domain of f inverse will have to be 5 to infinity, and the range of f inverse will have to be -infinity to 0, union 0 to infinity. Remember, the domain of the original becomes the range of the inverse. And the range of the original becomes the domain of the inverse. They trade x's and y's. If you're trading x's and y's, then you're, obviously your domain and range are trading. Okay, so they've given us an example here. They tell us f of x is this function and g of x is this other function. And they want us to verify that f and g are inverses. Now remember what we said. We said that if we find f of g of x, that has to simplify to be x, and g of f of x has to simplify to be x if they really are inverses. So they're telling us, hey, these are inverses. Just verify. That's like saying prove it. Show me that it's true. All right, so we're going to start out by finding f of g of x. That's the same thing as this notation. I just like this one better because people can see, oh yeah, x is closer to g, so it's going to go into g first. Okay. All right, so what is g of x? Well, g of x is 1/2 x minus 3. What are we going to do with 1/2 x minus 3? We're going to put it in the f function. So it's like if I told you to find f of 4, you would do 2 times 4 plus 6. You would replace x with 4. But we're not replacing it with 4. We're replacing it with 1/2 x minus 3. So I'm going to rewrite the f function, but instead of x, I'm going to put 1/2 x minus 3. So I wrote 2x plus 6, but in the place of x, I put the g function, the 1/2 x minus 3. I'm going to clean this up. I'm going to simplify it a little bit. So I'll distribute the 2. 2 times 1/2 is 1, or 1x. 2 times negative 3 is negative 6, and then I have a plus 6. Negative 6 and positive 6 cancel and leave just plain old x. This is good. Remember, we said that if f and g are inverses, then f of g of x better simplify to be x. That's what just happened. Okay? But it's not enough just to do it one direction. We have to do it the other direction as well. In other words, I have to find g of f of x. So now I'm putting f of x in the g function. Well, the g function is 1/2 x minus 3. But instead of x, I'm going to write the f function. F function was 2x plus 6. Sorry, I got a little ahead of myself. Oh, good grief. Keep getting ahead of myself there. G of f of x. F of x is 2x plus 6. So I'm going to take that 2x plus 6, and I'm going to stick it, that's my f of x, 2x plus 6. I'm going to stick 2x plus 6 in the g function. My g function is 1/2 x minus 3. So I'm going to write 1/2 x minus 3, but in place of x, I'm going to put 2x plus 6. So there's my g, my 1/2 x minus 3, but in the place of x, I put f, 2x plus 6. Okay? I'm going to clean that up. I'm going to distribute my 1/2. 1/2 times 2 is just 1x. 1/2 times 6 is 3. And then I have my minus 3 hanging out. 3 and negative 3 cancel and leave plain old x. Okay, so what have we done? Well, f of g of x worked out to be x, and g of f of x worked out to be x. Both things happened. So yes, f of x and g of x are inverses. Okay. Now, one other thing I'm going to point out about that I think is kind of interesting that is worth pointing out now. We're going to explore it a little bit more later. Let's graph this. Let's graph the 2x plus 6. Okay. Now, hopefully you know that this is going to be a line. The y-intercept will be 6 and the slope will be 3. So when I graph it, touches the y-axis at 6 and it goes up 3 over 1 or down 3 left 1. But that's a line right there. Okay. If I graph 1/2 x minus 3, that's also a line. The y-intercept is negative 3, and the slope is 1/2, meaning it goes up 1 over 2. And I'm actually going to change one more thing. I'm going to zoom square this. You don't need to worry about that. I'm just going to square it up a little bit, make my tick marks all uniform. Okay? And you're like, whoop-dee. Okay, there's 2 random lines. What's interesting is anytime you graph inverses, they are mirror images over the line y equals x. And here's what I mean by that. Remember, inverse means trade the x and y. So the point 0.06 that was on the original for f of x, take the point 0.06, that means it's the point 6, 0 on the g of x function, the inverse. We traded all the x's and y's. On the g of x function, we had the point 0, 3. I'm sorry, 0, negative 3. That becomes negative 3, 0 on the f function. Okay, so what happens is this line, this black line I just graphed in the middle here, is the line y equals x. So it goes through 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, etc. because x's and y's are all the same. What happens is when you graph inverses, they end up being mirror images over the line y equals x. If I folded my paper over y equals x, these points up here would match these points right here on the red. These points on the red here would match the blue ones if I folded it over. And that is always what happens when you're dealing with inverses. Okay, let's try another one. Here's f and here's g. Let's see if they're inverses. If they are, then f of g of x should simplify down to be x. Let's see if that's what happens, okay? Well, we're going to take the f function and we're going to stick g in it. G was 1/3 x minus 2. So 1/3 x minus 2 is going to have to go in the f function. F function was 3x minus 6. So in place of x, I'm putting 1/3 x minus 2. There's my plus 6. I'm going to distribute the 3. 3 times 1/3 is just 1x. 3 times negative 2 is negative 6. Plus 6, sure enough, that simplifies to be x. Okay. Now we got to try it the other way. We got to find g of f of x. Okay, well, f of x is 3x plus 6. Start on the inside. Now I'm going to rewrite g of x, and everywhere there's an x, I'm going to put 3x plus 6. Distribute the 3. 1/3 times 3x is x. 1/3 times 6 is 2. 2 minus 2 is 0. They both simplify to be x, so yes, they are inverses. Okay, if I graphed both of these equations right here, the graph would look a little bit different, but they would be mirror images over the line y equals x. Okay, number 3. Two different functions. Let's see if these are inverses. Let's find f of g of x and see what happens. Well, g of x is 5x plus 1. Start with the inside. We're going to stick 5x plus 1, the g of x, in for x in the f function. So instead of that x, I'm going to write 5x plus 1. And then I still had a plus 1 divided by 5. Okay. Well, let's see. I can add the 1 and 1 and get 2. 5x plus 2 divided by 5. We kind of want to cancel those 5s, but we can't. If I cancel those 5s, I'd also have to divide 2 by 5. This is not going to simplify down to be x. Okay? This is not going to simplify down to be x. That means f and g are not inverses of each other. But let's just do the other way just to verify. Let's find g of f of x. Well, f of x is x plus 1 over 5. I'm going to stick that in place of the g's x. So 5x plus 1, but instead of x, I wrote x plus 1 over 5. Okay, well, this x plus 1 is getting divided by 5 and then multiplied by 5, so that cancels and leaves x plus 1. But I still have another 1, so it simplifies to be x plus 2. Okay, so we got a problem. They did not simplify to be x, but they also didn't simplify to be equal to each other. In order to be inverses, they both had to simplify down to be x. So no, these are not inverses. Okay, they are not inverses. They did not have their composition functions work down to be x. Okay. All right. So we know how to verify if two functions are inverses or not. What if I just gave you a function and said, hey, you find the inverse? Oh, by the way, what if I graph that? Let's try that. Okay, so I'm going to graph x plus 1 over 5. And the other one is 5x plus 1. And then I'm going to leave that y equals x so that we can see if it's mirror images over it. There's the original. And it's kind of hard to tell. Let's try zoom square, see if that makes it a little easier. Sort of tough to tell, but they're not mirror images. If I folded it over the line y equals x, they would not match up. It'd be close, but not perfect. I know it's kind of hard to tell, but they would not match up, okay? It'd be a little bit off, okay? All right, so here's what's going to happen next. They're going to give us equations, like they're going to say, hey, find the inverse of this. So we're not just checking to see if two functions are inverses of each other. We actually have to find it. And so that's a 4-step process. I think there's a couple homework questions or maybe a lab or something that says use the 4-step process to find the inverse. And so let's talk about what those steps are, okay? The 4 steps are to replace f of x with y. Then we will interchange or swap x and y. Because remember, inverses, we trade the x and y. Then we'll solve for y. We'll get the y by itself in the new equation and replace the y with f inverse of x. Remember that little notation, -1 means find f inverse. Okay? All right, so here's this one. Now, if you wanted to, some people might prefer to call this y equals 1/2 x plus 2, just because they like more of the mx plus b format. Okay. If you'll notice, they've given us that same graph over here. This is a line, y equals mx plus b. The y-intercept is 2, and the slope is 1/2, so it goes up 1 over 2, up 1 over 2, etc. Okay, so they've given us the graph. They didn't have to do that, but they did. Just for fun, just to kind of get it out of the way, let's talk about the domain and the range. The domain of this graph, well, it goes left forever, right forever, so -infinity to infinity. And the range, how low to how high? Well, again, from -infinity up to +infinity. Okay. Let's find the inverse. Well, step 1, they said, was to replace f of x with y. So instead of f of x equals 1/2 x plus 2, let's call it y equals 1/2 x plus 2. All right. Step 2 was to trade the x and y. So I'm going to call it x equals 1/2 y plus 2. At this point, I have found the inverse. I traded the x and y. This is the inverse. It's just that it's hard to graph things when it has x by itself instead of y by itself. So it will be easier for us to deal with if we get the y by itself. So in order to get this y by itself, we'll probably need to subtract 2. So x minus 2 is 1/2 y. And then to get the y by itself, we need to get rid of the 1/2. So we can either divide by 1/2, or I think multiplying by 2 is easier. So if I multiply the right by 2, I better multiply the left by 2. And that will get y alone. 2 times x minus 2 is 2x minus 4. Okay? And then the last step is instead of y, let's use the f inverse symbol. So f inverse is 2x minus 4. Okay? Now, here's why it's nice to use that little f inverse symbol. When we talk about f of x, we know we're talking about the original. When we talk about f inverse, we know we're talking about this one. If we use x's and y's, it could be unclear which one's the original and which one is the inverse. So that's why it's nice to use f of x for the original and f inverse for the inverse. Okay, let's graph this one. This is a line, so the y equals mx plus b. The y-intercept is -4. The slope is 2. That means it would go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. I could connect those dots. Now, notice, pretend that's actually straight. Sorry, my line's a little bit crooked there. The domain of this guy is -infinity to infinity, and the range is -infinity to infinity. So our domains and ranges swapped out. I realized because they were both -infinity to infinity, you can't really see any difference. But that's what happened. And one more thing I want to show you on that graph. If I graph the line y equals x, well, y equals x means whatever x is, y is the same thing. So if x is 0, y is 0. If x is 2, y is 2. If x is -1, y is -1. So if I plot those points, I get this line right here. And when we graph that line y equals x, it's a little bit easier to tell that these guys are mirror images of each other. Okay, this point at 0, 2 has a mirror image of 2, 0. This point of 2, 3 has a mirror image of 3, 2 right here. Those points would be mirror images of each other over the line y equals x. Okay, that's a little bit longer video, but I think if by doing that we can get the last video to finish the last part there in part 2.